Okay, guys, so today I just want to talk about the Riemann sum, and I'm sure a lot of students having trouble with the Riemann sum, the left endpoint, the right endpoint, the midpoint, and also this one getting involved with the definite integral. So as you may recall that anytime you want to find the area under the curve, that means we want to approximate the area of all the rectangle. If you try to approximate all the area of the rectangle, you'll get like a close approximation for the area under the curve. So to simplify the calculation of the integral, and here's the theorem that we need to apply. So if f is integrable on the interval from a to b, and then that the integral from a to b, f of x dx, it's the same as that the Riemann sum, the summation of f of xi times delta x. Again, f of xi is just the height of all the rectangles, and then delta x is just the width. So once you try to sum all the area together, from the first rectangle to the nth rectangle, you'll get the area under the curve. And the way to find out delta x is by using that the upper limit minus the lower limit divided by the nth rectangle that you want to divide it, and then xi. So normally that's the first position we want to put in for finding the height. So for xi, we do have a plus I times delta x. So depending on whether that you started with the left endpoint or the right endpoint. If you started with the left endpoint, we started with a. If you started with the right endpoint, then we started with a plus x times delta x, I times delta x. And then we finished that with that endpoint at b. So let's take a look at that one of the example. So express that the limit and sigma I equals 1 to the nth, xi to the power of 3 plus xi times sine of xi, and then the whole quantity times delta x. So as the integrals on the interval from 0 to pi. So solution comparing that the given limit with the limit theorem 4. So we see that they would be identical if we choose f of x equals x to the power of 3 plus x times sine of x. So we're given that a equals 0 and b equals pi. And here's the one. So integrate it from 0 to pi of x to the power of 3 plus x times delta x, sine of x times dx. And also, well, this one is just going back to the definition to define it, to definite integral. Again, f of xi. So with the little snowflake, this one is just like an initial position that we want to put in for the height. And then times delta x. So there's certain formula that I need to recognize. So for the sequences in series formula, especially for sigma. So for I, as you may notice that this one is just considered arithmetic, or arithmetic. You know, some people pronounce it arithmetic or arithmetic. And then, so that equals n times n plus 1 over 2. And the other one is like I squared. So it's n times n plus 1 times 2n plus 1 over 6. And then I to the power of 3, which is n times n plus 1 over 2, quantity to the power of 2. So those are the formula that you have to recognize before we expand any Riemann sum. And here's some of the other formula, the property. So n times c, and then summation c ai. So c is just a coefficient. We can always pull it out. And then once you see like ai plus bi, we can always separate them. So ai plus bi. And then also the difference, we can separate them and do it individually. And evaluate the Riemann sums for f of x equals x to the power of 3 minus 6x. So taking the sample point to be right endpoint, and a equals 0, b equals 3. And then we got 6 rectangles. So instead of using the integral formula, power rule, so here's the way that we're doing it. So first thing that you want to find out is that delta x, the width. It's an equal width. So it's b minus a divided by n. So 3 minus 0 divided by 6, so we got 1/2. And then since we noticed that we started with the right endpoint, so that means x1, instead of starting with 0, we started with 0.5, because that, according to the formula, it's xi plus a, or a plus xi, so we got 0 plus 1/2, which is 0.5. And then x2, so we add 0.5 again, so we got 1. and then 1.5, 2.0, 2.5, and then all the way we finish that at 3. And then the Riemann sum, so we just plug in that all the positions, 0.5, 1.0, 1.5, 2.0, 2.5, 3.0. Again, we want to find out the different height. The first rectangle, the second, the third, the fourth, the fifth, and then the sixth. And then once you find the height, and then don't forget to multiply that by delta x, which is 1/2. So this one, we can just use that as the greatest common factor. So once you add all the height together, just multiply by 1/2 or divide by 2. And here's what we found. So it's negative 3.9375. So notice that f, it's not a positive function, and so that Riemann sum does not represent the sums of the area of a rectangle all the time. But it does represent the sum of the area of the blue rectangle above the x-axis minus the sum of the area of the gold rectangle below the x-axis. So here's the negative. And you might be wondering, well, how come this part is being negative? Well, because that is underneath the x-axis. Area cannot be negative, but since you're subtracting it, so we do have the positive, and then the other part of it, it's negative. So once you try to summarize them all together, so it's going to be the difference of the positive and the negative. And within n subinterval, so we do have that formula, delta x. So that equals b minus a divided by n. So that's 3 over n. And also just follow through that the technique. So started with the x equals 0, and then x1, 3 over n, 6 over n, 9 over n, and so on and so forth. Again, the way that I end up with that 6n is just by adding 3n, 3 over n, every single time. And then, so that means xi would be 3i over n. So it just shows the pattern here. And then by using that, the Riemann sum formula, we do have limit, and then summations, I equals 1 to n, and then f of 3i over n times 3n, 3 over n. And then by using that, the limit property, or the definitions, or the property that we just gone over, so we just separate them. So we do have 3i over n to the power of 3, which is 27, n to the power of 3, I to the power of 3. And then this one basically just simplified it, multiplied the numbers straight across, 18 over n, I. And then 3 over n, since we do know that's the width, so we can simply put it out because that n is the constant, because n is going to be going to infinity. Okay, so simplified a little bit more. Again, n, we can always put it out. So n, 1 over n to the power of 3, or 27 over n to the power of 3. It's just a constant, so we can just put it out. And then this one too. And then by using the formula that we just mentioned before, so IQ, which is always considered n times n plus 1 over 2, and then the whole quantity square. And then if that's just I, so which is n times n plus 1 over 2. So basically using the formula. And you may notice that, so we just simplify the whole thing. So we just simplified it all the way down to 1 plus 1 over n, quantity square. And then the other one is 1 plus 1 over n. So taking a limit as n goes to infinity, so 1 over infinity, that turns out to be 0. So we just left with 81 over 4 for the first summation. And then for the second summation, we do have 1 over infinity. Again, it's 0, so 27 times 1, so we do have 27. And 81 over 4 minus 27, guess what that is? Negative 27 over 4. And then you want to divide it, convert that to a decimal, so it's negative 6.75. Okay, so that's the one we just found. Again, area of A1, and then plus the area of A2, so we got negative 6.75. So this figure 7 illustrates the calculation by showing the positive and the negative terms in the Riemann sum, Rn, for n equals 40. So you might be considering dividing the area of the curve with many rectangles as possible. Well, that would be the best approach, but the better approach would be using the integral. Okay, so eventually it's pretty close. It's negative 6.3998. So the more rectangle that you have, the better the approximation that's going to be. So 40, 100, 500, 1,000, 5,000. So the 5,000 one, so this one is getting close to the final solution. And here's the midpoint rule. So we often choose the sample point xi to be the right endpoint with that ith subinterval because that is convenient for the computing the limit. But if the purpose is to find approximation to an integral, it's usually better to choose xi to be the midpoint of the interval. So the midpoint rule would be the even like a better approximation. So which we denote that by xi with a bar. And here's the midpoint rule. Since we do know that's the midpoint, whatever the endpoint that you find out, so you want to take the average of that value. So we got x1 bar, x1, x2 bar, x3 bar, so on and so forth. So the way to find a midpoint, it's always x1 plus x2 divided by 2. Or in general, it's x sub I minus 1 plus x sub I divided by 2. So here's the one of the example for using the midpoint rule. So you may notice that, so we need 5 rectangles. And it's going all the way from 1 to 2. So again, first thing that you want to find out, it's about the endpoint of the subinterval. So we got 1, 1.2, 1.4, 1.6, 1.8, 2.0. And so the midpoint in between 1 and 1.2, we got 1.1. The midpoint right between 1.2 and 1.4, we got 1.3. And the midpoint right between 1.4 and 1.6, we got 1.5. And then so on and so forth. 1.7, 1.9. So using that the midpoint rule, another thing that you want to find out, it's about the width. So the width for that, again, using the exact same formula that we just mentioned about. So we got b minus a over n. So it's 1/5. So the midpoint rule, given that delta x times f of 1.1 plus f of 1.3 plus f of 1.5, and so on and so forth. And doing the evaluation, so we got 1 over 1.1, 1 over 1.3, 1 over 1.5, 1 over 1.7, and then plus 1 over 1.9 times 0.2, or 1/5. So eventually, it's about 0.691908. So you may notice that instead of using more rectangles, so it's better to use the midpoint rule, because that would be even like a better approximation. And again, so here's the curve. It's a declining curve, so this one goes all the way from 1 to 2. So using the midpoint rule, so we can find out the area under the curve. So here's some of the property of a definite integral. So when we define the defined integral, integrals from a to b, f of x dx, we implicitly assume that a is less than b. But the definition as the limit of the Riemann sums makes sense even that a is greater than b. And notice that if we reverse that a and b, then delta x changes from b minus a over n to a minus b over n. So therefore, so here's that, the equivalency. So let's say that a is greater than b. Okay, if we try to reverse it, it's going to be the negative part. So negative times negative, which is what? Positive. And here are some other properties of a definite integral, and then this one also can be found from the textbook. Okay, so for the coefficient, we can always put it out. And then for the property, if that's summation, we can always separate it and try to integrate it separately. And then coefficient with the function, we can also pull out the coefficient. And then subtractions, again, we can always separate it. So thank you for watching the video today.